Okay, we're in chapter 12, which have to do about capacitors. And capacitors could look something like that, or they could look something like this. If it mattered which side was, if it doesn't matter which side's plus, which side's minus, they look like that. And if it matters, then they look something like that. Capacitors store charge. As soon as I get to that point, I'll let you know. So if I have an inductor, the inductor is storing a magnetic field. The capacitor is storing charge. Now, an electromagnetic wave goes in one direction. The electric field goes one way, and the magnetic field goes 90 degrees out of phase. And this is a three-dimensional thing. So this guy here is the black guy is going on. This is the y-axis. This is the x-axis, and then the z-axis is going that way. And so the green guy is going up and down parallel to the z-axis, and the black guy is going back and forth x, y direction. Right. So, and that's why, because the magnetic field and the electromagnetic wave, the magnetic wave is 90 degrees out of the electric wave. While they're both moving that way, you can now polarize your antennas to pick up one or the other or do something else. But the capacitor is storing charges, but the inductor is storing a magnetic field. So those are two different things that are going on.
You said the black guy was what?
Now, the question was, doesn't matter. Yeah, basically. So positive, that's on that side for those that want to know what positive is. I can also have a capacitor that's variable. So I have components with variable capacitors, and I can tweak on them. And so that's a possibility as well. I make a capacitor by having some area. So I have some area associated with something. And I could have, between them, I could have air, or I could have a dielectric. Dielectric. D-I-E. D-I-E. So if I have some dielectric in the middle, it's going to be at the same volume of capacitor is going to be able to store more charge. The capacitor is going to discharge really quick if I go and I ground it out. So there's big capacitors inside an old model TV that are charged to 30,000 volts. If you put your fingers across them, they can discharge really quick. And you would know that. So I've got some battery, and I've got some switch, and I got some capacitor. I close the switch, and now my charge flows in the capacitor. The capacitor is an open to DC current. So what happens is that I get a positive charge being stored on this side of the capacitor, causing a negative charge to appear on the other side of the capacitor, but the charge on the battery does not flow through the capacitor. It's that's an open. If I go and open my switch, now the capacitor is charged, and if I go and I shut my switch and I ground this guy out, then my capacitor will discharge. The charge will leave the capacitor, and the capacitor will no longer be charged. So if I have a capacitor and I think it's charged, I want to discharge it, I just take a screwdriver, put it across it, and get rid of the charge. Everything will be fine. A capacitor has a capacitance, which is measured in farads. F-A-R, farad. How do you spell farad?
F-A-R-A-D-S.
A-D-S? All right. So my capacitance is going to be whatever the charge on the capacitor is divided by the voltage. The capacitance is going to have a unit of farad. The charge, the unit of charge is going to be coulomb, C-O-U-L-O-M-B. And voltage is going to be voltage. All right. That seems reasonable. 1 farad is 1 coulomb per volt. And that's relatively new. The idea of having capacitance didn't occur probably until 1850 or so. Before 1850, you wouldn't think of having capacitance. It wouldn't have occurred. So Newton would have had no idea that capacitance existed, and Newton probably didn't have any idea that inductance existed either. Both of those are relatively modern to the human existence.
That or if he knew, he didn't tell him about it.
Yeah. All right. The capacitance of my capacitor is going to be epsilon naught A over D.
What's that symbol?
That's an epsilon. Don't you know your Greek alphabet? Typical.
I barely know the Mexican. You think I'm gonna know?
The book calls it 8.85 times 10 to the minus 12th epsilon relative A divided by D. Let's see, what's epsilon naught anyway? Well, without my physics book, I wouldn't know. So epsilon relative is the relative permeability of the dielectric. 8.85 times 10 to the minus 12 is the permeability of a vacuum of an electric charge. C is capacitance. A is area. The area is going to be in meters squared, and the distance has to be in meters if I'm going to use that particular equation. So clearly, I'd rather just go and measure the voltage and know the capacitance and get the charge. That would be my choice, right? If I was going to do something. But somebody has to manufacture these things, right? So if I want a 1 microfarad capacitor, which I may very well want, I'm going to have to know how I'm going to make it. So that's what I'm going to do. So capacitance 1 over, what is it? I don't know. I won't write it down. I won't confuse the issue with that. So now we have parallel plates. So we have parallel plates sitting here, and they have some area associated with them. We don't multiply the area by 2. You know, whatever the area is, 1 is, that's the area we use. And we can calculate what our capacitance is using the formula above. On page 368, we find the relative value of ER for material. So for air, it's going to be 1 and for glass, something almost 10, and anyway, paper 2.5. So my dielectric, we're not talking about increasing the capacitance by hundreds or thousands. We're talking about increasing the capacitance by some number less than 10, if I'm going to put a dielectric in there. Okay, enough of that. I have series circuits. In a series circuit, the voltage total is the summation of the voltages. The current total is whatever the current is. It has to go through everybody. The resistance total is the sum of the resistances. The power total is the sum of the power. The inductance total is the sum of the inductors. And the capacitance total is going to be 1 over C1 plus 1 over C2 plus blah, 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 1 over Cn. So in a series circuit, the capacitance acts the same. If I want total capacitance, it's going to act the same as resistance did in a parallel circuit. Now I look at a parallel circuit, and I see voltage total is the same as voltage 1, is the same as voltage 2. The current total is the summation of the currents. The resistance total acts as 1 over 1 over. The power total is the summation of the powers. The inductive total is 1 over the inductance. And the capacitance total is the summation of the capacitance. Now there's a mathematical thing I could do to show that, but I won't bother. Okay. Now, if I go all right. So if I have a battery and I put it in a capacitor in there, this guy's going to act as a short, as an open. If I have a battery and I put an inductor in the circuit, it's going to act as a short. If I go and put an AC signal into my capacitor, then what's going to happen is that as I increase the frequency, I increase what's going through there. So I end up with a DC frequency, no frequency at all. I have no current flowing, but as I increase the frequency, I end up being shorted out. So at high frequencies, this guy's going to be a short. He was an open at DC, he's a short at AC. Same thing is going to be true when, in a similar way, when I take that inductor. So the inductor will pass maximum, and then drop off. So as I have a short, I'm flowing maximum current, and then I get to some point and then I start dropping off and I do less and less. If I look at X sub L, that's 2 pi FL. As I increase the frequency, frequency goes up, X sub L goes up. When I take and look at X sub C, it turns out to be 1 over 2 pi FC. So when my frequency goes up, my capacitive reactance goes down. So I look at this as an open at DC. As I increase the frequency, this becomes, the inductive reactance starts going down. I end up passing more current. So that's what's happening there. Now, from a calculus point of view, the current across the capacitor is going to be the capacitance dV dt. So change in voltage, change in time, times capacitance is going to be what the inductive voltage is. So if you remember the current in an inductor, we don't. The voltage across the inductor, L di dt. So change in current, change in time, times the inductance is the voltage across the inductor. The current in the capacitor, C dV dt. Back to Eli the Iceman. In an inductor, the voltage leads the current. In a capacitive circuit, the current leads the voltage. Okay, so that's what the ice part is about. So on page 374, I see that relationship being pointed out. Oh my goodness, on page 375 it actually says Eli and ice. I don't believe it. It says Eli the Iceman on page 375. I don't believe it. Oh, look at that. Halfway down the thing there. Wow, that's so special. Okay. So when I look at my real and imaginary plane, I find that my x of L is going to be on the imaginary axis in the plus direction, and my x of C, my capacitive reactance, is going to be a negative I value. It's going to be below the R axis. I can solve for x of C by taking the voltage RMS in the circuit, dividing by the current RMS. I can find it that way. Or I can say x of C is 1 over 2 pi FC, and I can calculate it that way. Once I have my reactive capacitance x of C, it's a value that is in ohms, and now I can treat that x of C just as I would be treating resistance. So although if I come back to this guy here, I have XC capacitance total follows the 1 over rule. X sub C total would not follow that rule. That'd be X of C1 plus X of C2. And in a parallel circuit, the same thing would be true. X sub C total would be 1 over X of C1 plus X of C2. So once I've calculated the capacitive reactance X of C's, I would then do the math just like I would do resistance, keeping in mind that it is at a minus 90 degree angle. So I may have to deal with the minus 90 degree angle, but as long as all I have is capacitor reactance, I can drop the angle and add it at the end, because it's going to be, if I bring it with me through the whole calculation, I'm still going to be at minus 90 degrees when I get done. For the physics guys in the room, you could say my angular velocity is 2 pi f, and I could say x of c is equal to 1 over omega c. Not particularly useful because I'll get rid of that guy, because you're going to remember it the other way. Ohm's law still applies, so Ohm's law could be there as well. Oh, well, I guess we're done, except for working problems. Okay, we'll look at number 2. Oh, that won't work. Number 2. The capacitor is storing, so I got my capacitance is 100 microfarads. And the voltage across it is 40 volts. Calculate the value of the component. Calculate the value of the component. A capacitor is storing that. Oh, okay, right. Okay. Read the problem. Somebody come up here and take the whatever it is off my so my charge is 100 microcoulombs. My voltage is 40 volts, and capacitance is charge divided by voltage. So if I have 100 microcoulombs divided by 40 volts, then that should be 25 microfarads. Did I do that right? Yeah, I think so. So that's all there is. There ain't no more.
40.
Oh, I'm sorry, 40. 2.5 microfarads. We'll take out our glorious calculator. 100 divided by 40. 2.5. Microfarads. Farads. Farad. Now, something the size of about that big, that would be a 1 microfarad capacitor. A farad capacitor is going to be the size of this desk. Okay, and in an industrial setting, you're going to have a capacitive bank to change the power factor of the plant. Then that capacitive bank is going to be a quarter the size of this room, and it's going to have high voltages in it. It's going to be locked, so no one can go in. That's right, because if you go in that room, you're going to be fried very quickly.
Exactly.
All right.
Just like your watchman. So how do you ever go and fix some shit like that?
I'm looking at problem number 5. Calculate the total capacitance in the circuit A. All right, so I got 1, 2, 3, and I want total capacitance. All right, 10 microfarads, 220 microfarads, 330. I thought sure I could do this one in my head, but no, author thing. Now, the same rule applies in resistance. In resistance, if they were in parallel, then the total resistance would have to be smaller than the smallest resistance, right? So capacitors in series, following the same rules as resistors do in parallel, the answer's got to be less than 10 microfarads for this guy. Okay, so it'd be 1 divided by 1 over 10 micro, 1 over 220, 1 over 330. Now what I'd put in my calculator would be a 10, 1 over key, plus 220, 1 over key, plus 330, 1 over key, equals 1 over key, and then when I got done, I'd write microfarad next to it. Now, I could do it a different way. I could find a common denominator and add and flip it, right? But that's not what we are. 10, 1 over, plus 220, 1 over, plus 330, 1 over, equals 1 over, and I have 9.3. So my total capacitance 9.3 microfarads, which is smaller than the smallest one, and I'm happy. If these guys were all, if I had a 10, a 10, and a 5, for example, well, the 10 and 10 would make 5, the 5 and 5 would make 2.5, just like it would if I had resistance in parallel. So I could use the same rules. That was number 5. Number 9. Number 9. Notice how all the math you do, you just continue doing the same thing over again? You notice that? So if you didn't learn it the first time with resistors, you learned it with inductors. If you didn't learn it with inductors, you got to learn it with capacitors. And by the time we do it 3 times, it's almost halfway to the 18 I need. All right, number 9. Calculate the total capacitance in 26A. All right. Could I put this in multisim and hook up a capacitance meter?
Sure.
No, doesn't exist in multisim. Okay, so this is a 22 microfarad, 33 microfarad. Capacitance total is 55 microfarads. My pen never left my finger never went to my calculator or anything. Yeah, let me think about this. Oh, okay. I'll think about it. Remember in the last test, you had resistance in series and parallel, a page of each. On the next test, you're going to have a page of inductors in series, inductors in parallel, capacitors in series, capacitors in parallel. Yeah, so that's what I expect now. Unless I go and make a new test, which ain't going to happen. Number 19. Determine whether or not a 50-volt capacitor can be used in the circuit shown below. All right, so I got an AC circuit that's 42 volts, and I got one lousy capacitor. That's all there is, C. And capacitors have voltage ratings. So I have 50-volt capacitors, 100-volt capacitors, 43-volt capacitors, all kinds of different sizes. In fact, we went and we were fixing a TV set last spring, and we didn't have the right size. We had the right size capacitor for capacitance, but not for voltage. And I ordered the right ones, and some of my glorious students decided to go scrounge through the parts, and they found a different one. Instead of, I needed 250 volts, 450 microfarads or something. They found some 100-volt ones that were the same 450 microfarads, and they wanted to know if they could put them in. And I, sure, why not? Yeah, no sweat, you know. We all have safety glasses on our glasses, right? Yeah, all right. And anyway, they put them in, they plugged it in. It only took 2 seconds for them to blow. It was really great. And it blew the entire guts of the capacitors all over the lab. It was just one of those things. It had to be there. So the voltage, yeah, it had to be there. The voltage has to be what it has to be if you put in the wrong size voltage. So the issue is 50 volts good enough? If I have a 50-volt capacitor in a 42-volt system, is that good enough? And I think we have to vote on it, right? And whichever side gets the most votes, I will declare them wrong. Right? Isn't that the way it always works? Yes, no. Okay, how many say yes, that'd be perfectly okay? 1, 2, 3, 4. 4. How many say, no, I would never do that in my entire life? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And I say, no, I won't do that. All right, now, for the guys that say yes, I know why you're saying yes. For the guys that are saying no, why are you saying no? Other than the answer is always different than what the reasonable answer is.
The voltage is coming out of the.
Yeah, that's the issue. The issue is the 42 volts is an RMS voltage. Why? Because it doesn't say it's not, right? In order for it to be other than RMS, it would have to have a P there, or a P to P there, right? Well, what is the peak voltage of this circuit? Square root of 2 times 42, which is what? 57, 53, 50, something greater than 50. Square root of 2 times 42, 59 volts. So, no, it would not be acceptable to have a 50 volt capacitor in a circuit where the peak voltage is going to be 59 volts. Now, is it going to fail in 30 seconds or less? Probably not. Probably won't. Probably won't fail until the most inconvenient time. So, you put it in your nuclear weapon system and you launch your nuclear weapon and just, like 30 seconds over target, it fails, and now your multi-dollar nuclear weapon doesn't blow up. So, yeah, that would be a relatively important thing. Well, that was 19. Can we even do 24? I don't know. 24. Nope, can't even do 24. All right. So that means we'll have to go back and do some more problems. Well, or we can go vote.
No problem.
You need to go vote?
Yeah.
You really do?
Yeah. Our country depends on us.
Oh, yeah? Well, not if you're going to go vote in Nebraska. It's already settled there. It was settled there last, The primary elections settle who's going to win the general election in Nebraska, right? So we already know that Debbie's going to win, yeah. So that, huh?
Some red state.
All right, Control, Alt, F12.